Okay, let's get to it here. 10.1, day number 1, notes. Today's material, we'll be discussing the three trig ratios, Pythagorean theorem. Most of this should be review. Maybe a couple twists in there for you just for fun. This is the first day of the semester, so a couple of expectations. You could pause the video and read these. Most of them are pretty much straightforward. I think the last one up here takes care of it. If you're a quality person, the rest will kind of fall in line. Just kind of do what you're supposed to do and get things done in time so that you have more time to do what you want to do instead of spending extra time on making stuff up and I don't know, just be a quality person. All right, let's get right into it. Trig ratios. There's three trig ratios that we're going to work primarily with to begin with, which are sine, cosine, and tangent. And it's interesting. They come from Pythagorean theorem right over here. Right, here's our hypotenuse, and here are the two legs of a right triangle. And we know that a squared plus b squared, this got drilled into your head in middle school, some of you kindergarten, but a squared plus b squared equals c squared. Something kind of cool comes up when we put this into the unit circle format. Unit circle, of course, is a circle that has a radius of 1, which becomes our hypotenuse, which will always stay the same in the unit circle, whether or not my triangle looks like this, or like this, or like this. All of those items would still have a radius of 1, each of those triangles, but their sine and cosine would change. So what we can see here is that theta, our angle, right here, there are certain ratios provided. We call this the sine value right here, and that is the y value of this point. And the cosine is the x value. So cosine is going to be our x, and sine is going to be our y, and tangent will be, of course, we know tangent is opposites over adjacent. Let's get back to this for a second. Sine is opposites over hypotenuse. But if the hypotenuse is always 1 in the unit circle, then it's just the opposite side, which becomes the y value, or the output value of that certain input. Cosine is adjacent over hypotenuse, which is always 1. And tangent is opposite over adjacent. Well, opposite, we said, was y, and adjacent was x. So the sine value is always the y value, or opposite over hypotenuse. The cosine is the x value, or adjacent over hypotenuse. I'm going to put this opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. We'll use both of those forms here. And interesting fact, later on, we'll see that cosine squared plus sine squared always equals 1. Leg squared plus leg squared equals hypotenuse squared. All right, let's keep moving. All right, so a few special right triangles, jumping to a different topic. Special right triangles, we're going to get either 30, 60, 90, or 45, not 445, 45, 45, 90. And those are our special right triangles, and we typically work with those in the unit circle. Looking at this example up here on the northwest portion of the page, if those two are x, you may or may not remember, but we would take x times the square root of 2 to get the hypotenuse. Over here, it's clear that I have a 60 here, so therefore this angle must be a 30. Because the three angles in a triangle, 2 and 3, they must add up to 180. So I've got myself a 30, 60, 90. And some of you may or may not remember, but the short side, this is the shortest leg, because it's across from the 30, will always be 1/2 of the hypotenuse. And we would always scale that short leg by the square root of 3 to get the long leg. If you want to, you can pause the video and look at the next two. See if you can come up with those values. All right, unpause. This is going to be a 45, 45, 90, so the two legs will be the same. And the hypotenuse would be said thing, 11 root 2 times the square root of 2, which can be simplified to 22. How did you do that? Well, the square root of 2 times the square root of 2 is 2. and 11 times 2 is 22. So that would be our hypotenuse length. Okay, in this example over here, I've got myself a short leg of 10. That means the hypotenuse will be double that. And that short leg times root 3 would give me the other leg. Okay, let's keep moving. Determine the unknown sides of these lengths. All right, go ahead and pause the video. And when you come back, you'll see some answers. All right, guys, let's take a little gander at these answers. First one here, it looks like 45, 45, 90, 16s for both of the sides. So I'd multiply that by root 2 to get 16 root 2. I was given one of the legs here in a 45, 45, 90. That'd be equal to that. Therefore, I'd multiply that by root 2. Square root 5 times square root 2 is square root 10. Cool. Let's see here. A couple of possible answers here in the answer to the west. I'm given the hypotenuse now on an isosceles right. Isosceles right meaning isosceles, two sides the same, right triangle. Fact, equilateral right triangle, not possible. Okay, so don't try it. I have to divide by the square root of 2 to get one of these two sides. And of course, this is an acceptable answer. That's fine. It's kind of JV, but it's fine. You won't be penalized for leaving in that form, but this would be a rationalized version of that. So either of these two answers right here or here would be acceptable for that. Okay, over here, given hypotenuse, oh, this is a nice one. Don't make too much work out of it. Okay, divide by the square root of 2, what do you get? 25. Okay, so your sides are 25. Let's keep rolling. Given this side here, I would divide by the square root of 3, right, and I get 12, right? I'd be 12 square root of 3 divided by the square root of 3. Those would cancel. I get 12, and I'd double that. To get 24. Okay, and the last one, kind of sneaky, depending on what form you put it in. I'd be okay with JV though if you left it that way. Divide that in half. All right, 18 divided by 2 is 9, and then multiply that by the square root of 3. Well, square root of 3 times square root of 3 is 3, which makes 27. Oh, I wrote that there. That's cool. All right, I think I've got a little bit more to do here. This would be a challenge problem. You can work on it on your own. Actually, I'll pause and I'll give you the answer to that. All right, I decided not to give you the answer right away, but ABCD is a square, so I've marked that appropriately. BAE is 30, so BAE is 30, this angle. So that makes this angle right here 60. Okay, so that makes this angle right here 60. That makes this angle right here 30. Notice how I've geometrically marked these how they should be. Vertical angles would tell me that's 60 as well. So I got a bunch of special right triangles here, all 30, 60, 90s. Let's see what else I know. BA is 30 and DE is 12 root 6. DE is 12 root 6. What am I trying to find? Area. Okay. Okay, so I know, was it DE? DE is 12 root 6, I think that's what I said. Yep, DE is 12 root 6. Okay, so this length is 12 root 6. Oh, I see. All right, so what would this length be? Well, it would have to be half of that, which would be 6 root 6. And I want the area of the square, I believe, yeah, area of the square. Well, area of a square is side times side. And this square in particular has a side of 6 root 6, which means this side would be 6 root 6, which means I'd have 6 square root of 6. I don't like the way that's written. Let's go, instead of side times side, how about side squared? Okay, which would be 6 squared times the square root of 6 squared. That's 36 times 6, which is 216 units squared. Sweet. All right, let's keep going. Okay, this might have been just too long ago, but the sine of 30, I'm just going to fire them out there. Sine of 30 is 1/2. Cosine of 30 is square root of 3 over 2. Tangent of 30 is going to be the, remember, this was our y value, this was our x value, this is going to be y over x. So 1/2 divided by square root of 3 over 2 is the same as times, that'd be 2 over square root of 3. Okay, I'm going to simplify that. 2's go away. I get 1 over root 3, which is fine. Or you could write this as the square root of 3 over 3. That'd be the tangent written. Well, yeah, I mean, that's the tangent of 30. Again, hey, you might or might not remember this, but 30 is equivalent to pi over 6 radians. 45, you can quiz yourself, but it's pi over 4, and 60 is pi over 3. Okay, and you're going to see a few values start to show up frequently. All right, this is going to be 1 over root 2, which commonly can be written in this form, square root of 2 over 2. The cosine is going to be the same, 1 over root 2. But the tangent is really easy. I don't want to divide both of these, but they are both the same. So technically, if I took square root of 2 over 2 times 2 over the square root of 2, I get 1. So the tangent of any pi over 4 or 45 degrees is nice. It's 1. All right, let's move on to the special rate using 60. Sine of 60 is root 3 over 2. Cosine of 60 is 1/2. And the tangent of 60 is going to be the square root of 3 over 2 divided by 1/2, which is the same as times 2. Those cancel. I get the square root of 3. There are some special values that you'll see in the unit circle. We'll get to more of that as the unit goes on. All right, now talking inverse tangent, inverse cosine, inverse sine. It looks like I've only required you on this page to use inverse. What would that be? Opposite over hypotenuse. So let's try to remember these. So ka toa. What does this mean? Well, it means that the sine of theta equals opposite over hypotenuse. The cosine of theta equals adjacent over hypotenuse. And the tangent of theta, theta being an angle, always an angle, is opposite over adjacent. So here's theta. I think we can all agree that this would be the opposite side. The side that's in question is this the adjacent side or is it the hypotenuse? Well, the hypotenuse is always across from the 90, so this would be our hypotenuse. So if I want to know the measure of angle theta, you can and will agree that the sine of theta would be the opposite over the hypotenuse. So if I want to know the measure of theta, I take the inverse sine of 10/26. Let's set up the next one, and then I'll bring up the handy-dandy calculator. Okay, same thing over here. Here's theta. Here's the opposites. Here's hypotenuse. Oh, I see something that you might not see yet, or maybe you do. But the sine of theta equals 5 over 13. Therefore, theta is going to be the inverse sine of 5 over 13. Now, I know that both of these are going to be the same. How do I know that? Well, because if you look at this ratio and you look at this ratio, what's true about them? Well, they're equal. So if the ratio of those sides are the same, then their angles are going to be the same. Take out your calculator. I'm going to pull mine out. I don't really want to type in a bunch of letters. Let's see what mode I'm in. I want to be in degree mode. Yeah, I want to be in degree mode. Let's do the inverse sine of 5. What was it? 13ths, I think. And it looks like I get 22.62 degrees. I'd say if we're rounding, we would go 22.6 degrees. Now, don't judge us teachers because the image that you see might not always be proportional to like this. That does not look like a 22-degree angle to me. This one looks more like 22, but just go with the numbers in the setup. It won't always be perfect. So that's it. We can talk through registration stuff later on. That's 10.1, day number 1 notes. Hope it goes well. Peace out.